today I want to finish this topic of quantifiers. So we only have a bit left to say about this. Okay. So now that we understand what quantifiers are, existential quantifier, universal quantifiers, the uniqueness quantifiers, remember that they are there to make propositions out of propositional functions. Okay. So we have these statements that are not really propositions. They don't have a truth value, but you put a quantifier on it, and they become propositions. The moment that they become propositions, you start to ask yourself several things. Like, for example, how do I tell whether these two propositions are equal? That's what we discussed last time. Logical equivalence between quantified propositions. Okay. Another thing that you would like to do is negate these propositions, right? When you have a proposition, you want to write negation. You want to see how to negate these propositions. So let's talk about that now. How do you negate quantified expressions? Okay. When you have a proposition with a quantifier, how do you negate it? And if you already saw it, then you will see it's pretty straightforward. Okay, it's pretty easy. But let's first do this example and try to use our common sense for us. And try to use our common sense. Thank you, Mr. Yep. So let's see. Let's read this statement. Every student in this class has taken a course in calculus. Okay. First of all, do you understand that this is a quantified proposition? Why?
For all. Every is for all.
Exactly, because the word every, right? So this word every here is telling you that we are in the presence of a quantified proposition. Okay? So we're going to worry about the formalities later. The problem says do this problem in words first, so we're just going to use sentences now, and then we're going to do it using symbolic logic. Okay? So, but let's first come up with the answer using our common sense. So we have this statement. Every student in this class is taking a course in calculus. Let's write the negation of this statement. Let's see. What's the first thing that comes to your mind when, and be true to yourself. I mean, if you already know the answer, probably going to tell me already the final product. But when you need to negate something, what's the first thing that comes to your mind?
The opposite.
The opposite. How do you say the opposite in English?
Negation. What do you mean?
Okay, what's the this what? Okay, so this water bottle is black.
Yeah.
What would be the negation of this? What's the first thing? How would you negate that statement?
Water bottle is not black.
Okay, but that one already has a grammatical fix to it. Let's do something that is a little bit more generic. You could say,
Water bottle is white.
it could be pink, or the water bottle is not black. But another way to say it is that the words for everybody would be: it is not the case that the water bottle is black. Yes. So if you always say it is not the case, or you write something that indicates that you are negating what you're about to say, that's technically a negation, right? Because, for example, that grammatical fix of the water bottle is not black, we cannot really apply it to this statement. Okay? But we can do the it is not the case stuff. We can say it is not the case that every student in this class has taken a course in calculus. That fixes it. So if you say it is not the case and then you put exactly the statement that you're given, you're negating that statement. Do you understand what I'm saying? When you say it's not black, you're playing with the grammar of that particular sentence, which is fine, but it doesn't generalize. Everybody understand this? So let's write down that, I guess, universal way of generalizing a statement. So the negation, or you could say it is not true that, anything similar to it is not the case. Okay? So I would say it is not the case. Or just say, in short, not every student, right? It's the same thing. Did you see the movie Borat?
Yes.
Yeah. He liked to speak in this form. Like, he would say something, pause for a little bit, and then what he would say? Not. So what is he doing? He's negating whatever he said. He would tell you, this water bottle is white. And they would say, not. We'll go crazy for a while. I said, not. So, calm down. So after that, he's playing this game. Okay? He just typically we negate at the beginning, right? To avoid all of that interaction. So you can say it is not the case, or just say in this case, not every student, and that's kind of short. Okay? So I'm gonna go that way. But if you say it is not the case, that's fine. But let me just say, not every student, this is Borat style. Not every student in this class has taken a course in calculus. Everybody okay with this? All right, so this is the negation of that. But now let's play with this a little bit more, okay? Because if you were going to translate this symbolically, this would look like the not is the negation, and then we just have the statement that we have, okay? So this would be the negation of whatever, for all x, blah, blah, blah. But we don't want that, okay? We don't want to have this in front of quantifiers. We want to have this in front of the proposition of functions. So I would like to write this in another way. In other words, I don't want to begin with the word not, or with the one, or with the word it is not the case. So let's play with the English. How else would you say this idea? Now, having in mind the fact that I don't want this in front. For example, your classmate said the water bottle is not black. Instead of saying it is not the case that the water bottle is black, right? So I would like to have something similar to that. The is not, it has to be somewhere, right? The negation. But I don't want it to be at the beginning. I want it to be somewhere inside the statement. So how can we rewrite this? Not losing the meaning, right? So I want to write something equivalent to this. So let's think about what this is saying. Not every student in this class is taking a course in calculus. How else would you say this? So what does this mean?
There are students who did not take calculus.
Very good. Does everyone understand this? What we're basically saying here is there are students, or there is at least one student. It doesn't have to be, maybe there is only one. Okay, we don't know. But what we can say for sure is that this means that there is one student, or there is a student who has not taken calculus. Does everybody agree with this? Carry the same meaning, but then we remove the not from the beginning and we put it somewhere in the middle. And in the process of doing that, what just happened? Here we have the every quantifier that we're in universal. In the process of moving this guy inside, what just happened in a sentence? What quantifier pop up? The existential. Do you understand this? And this is a general fact. When you negate a universal, it turns into an existential state. Okay? But then you have to negate the predicate part. So we're gonna formalize it now. So not everything in this class taking a course in calculus. Equivalently, you could say there is a student. I don't want to say there are students because maybe there is only one, right? So if there are two, fine, but there is at least one. So there is a student in this class who has not taken a course in calculus. Do you understand this? It is clear? Okay, so those two things are the same. They are both negations, but this one has the advantage that it doesn't have, it doesn't have the border style stuff. Okay, it doesn't have the not at the beginning. All right, so let's write this now formally using symbolic logic, and then we will tell you exactly how is it that we negate this type of statements. Okay, of course, similarly, if you want to think backwards, for example, right now you know that if I negate this statement, what am I supposed to get? Let's see, let's go here. If I negate this statement, what am I supposed to get? No, the one that I'm pointing at. Which one? Which one? I cannot hear. Say loudly. Louder.
Can you rephrase the question?
If I negate this statement that I'm pointing at, what am I supposed to get? The original statement. Remember, negation of the negation is the original statement, right? Well, but this is the same as this, right? So if I negate this, what I'm supposed to get? The original statement. In other words, the negation of a universal is an existential, but if I negate an existential, what do I get? A universal. Okay? So a little example tells you the two special rules. The negation of for all is that exists. The negation of that exists is for all. All right? But now let's see how that rule works out, and to see the details of that, let's dissect this example more. Let's write it formally, which is, we did it already in words. Now we're gonna do it using symbolic logic, okay? Now, because we see this is universal, there are some things that we need to do. First, we need to establish a domain, we need to establish a predicate, a variable, and all that business, okay? All right, so formally, let's see, what do you think would be our domain?
Students. Or
Students in this class, right? We are not really talking about students outside of this class, so the students in this class. The students in this class. Okay, that's a domain, so students in this class. And then when I say X, I'm talking about a particular student of this class, okay? A student in this class, when I say X, that's what we mean. Now, we need a predicate. So what do you think P of X would be? A predicate that matches the situation. So what should be our predicate?
has taken a course in calculus.
So X, a student X has taken a course in calculus, right? So P of X stands for X has taken a course in calculus. Yes? Now, with this in mind, let's write the original statement. So, original statement now. What is it? How do I write it symbolically?
For all x, d.
Okay, so when you're doing the homework, this kind of thing happens, right? So this means for all elements in the domain. But because we already specified the domain, as I said before, I'm not going to be writing this stuff, okay? It's understood that we are only talking about students in calculus. This, you should do it when there are multiple domains in play. Like if you're doing a problem and there are several domains and you want to specify this is coming from here and this is coming from here, okay? The different sets, okay? For example, imagine that we have calculus and biology. Then maybe you have the domain of all sections in calculus, then all sections in biology, and then you have to specify the domain, and then you will have to say that kind of stuff. But here there's no ambiguity. So when I say for all x, it really means for all x in for all x in the domain. Okay, so for all x,
P of x.
P of x. Good. Does everyone understand this? This in symbols means the original statement. Every student in this class has taken a course in calculus. Yes? All right. So that's the original statement. Now let's write the negation. So the negation, which, as you know, that's the proposition. We have a symbol for negation, which is this, right? We have our proposition, and now we are negating that proposition. That's what I'm saying. This is a proposition, we're negating that. Notice that this is the same thing as if I had done this, okay? It's just that, as I said last time, a quantifier, they have higher precedence over everybody. So if I don't put parentheses, this quantifier is acting on P before you use this negation. So the parentheses will be done like this, okay? So we don't really need to put parentheses when you write this stuff. But if you want to make, you want to avoid discussion with somebody that probably doesn't know the rule, then just put parentheses and then move on. We're big guys, so we don't need the parentheses, okay? All right, so that's the negation, that's the symbol. For example, this corresponds to our first version of the negation, right? With the not in front. That's what we're saying. I'm negating whatever I'm about to say. That's what this is telling me, right? Now let us write the true version, or the nicer version without the not at the beginning. Okay? So what is it? Just rephrasing what is in there.
There exists x.
There exists x.
Not P of x.
Very good. Do you understand this? So what's the negation of P of x? If P of x means x has taken a course in calculus, the negation is x has not taken a course in calculus, right? So here we're saying there is a student in this class who has not taken a course in calculus. You okay with this? So now, forgetting about all of these examples and just looking at the symbols, in fact, just looking at this line right here, it tells you what's a recipe of how to negate quantifiers. And you negate a universal, what do you do? The for all turns into that exists, and then the negation passes through, and you have to negate directly whatever you have inside the predicate part. Okay? And then similarly, the other way around. If this was a that exists, then it becomes a for all, and you negate the stuff inside. Do you understand this? Questions? All right. So that little rule is symbolized here. Okay. So negation of for all turns into that exists, but then you have to negate this part. Okay, you have to negate it, otherwise it doesn't make sense, right? And then when you negate that an existential, it's the same thing. It turns into for all, and you negate the predicate. Are we good? All right. Then let's try these examples. So you could do this without me giving you a domain, but the reason why I'm giving you a domain is just because I want you to compare truth values then. To make sure that the negation is correct, the value of the truth value of your result has to be the opposite of the original, right? So let's use that as a checking point. But mechanically, you can do it. For example, let's do the first one together. So the negation of for all x, x squared is greater than x. What would this be?
There exists x.
There exists an x.
Where x is less than x squared.
Okay, that's exactly what that says. X squared greater than x means x is less than x squared. You have to negate that. Okay, let me do another step. So negation of this, right? You do it mechanically, like a computer, without thinking. What do? Turn for all into that exists and then pass the negation through. That's the first step. But now, we're not a computer, we're humans. So we say more. So what does this mean? Now we know a concrete predicate, so let's rewrite this. What's the negation of x squared is greater than x? So I guess the question is, how do you negate greater than? That's really what we need to negate here. Are you sure? Less than or equal to. Right? Do you understand this? It's less than or equal to. If you have greater than or equal to, then the negation is just less than. Okay? So be careful with that. So that exists x such that x squared is less than or equal to x. Because remember, equality here will also turn this into a false statement, right? Yeah. So you have to put in your negation. Okay? The opposite of greater is less than or equal to. Okay? All right, do you understand this? I mean, the process itself should be pretty straightforward. You see a for all, you negate it, turn into a that exists, but then you have to negate the stuff in the value. Okay? Now let's see, let's analyze the truth values. What's the truth? Now let's focus on the domain. Notice that we don't need the domain to do this. Yes? To do this negation business, we don't need the domain. But now if you want to see what the values are, you do need the domain. You need to know what is this x. Okay, our domain is the real numbers. And by the way, this is the symbol for the real numbers. It's like a bold face R. Okay? Okay, so the original one, what is it? Is it true or is it false? False. Good. Why?
0 or 1.
Exactly. So for example, you can pick 0. 0 squared is equal to 0. So, and remember, this is universal. Just give me a counterexample. That's what you need. Just tell me one concrete case that is false, and then that makes it fair. Very good. And how about that one? Let's see, what are we expecting to get?
True.
We're expecting to get true, right? Because the negation of false is supposed to be true, right? Let's see, convince me. Why is this true? Other than obvious, it's the negation of value.
Also true.
So to justify that an existential statement is true, you just have to give me an example, right? An example in which it works. So 0 works, right? Because 0 makes this work. There are many that makes it work, but 0 makes it work, so you're good to go. Okay? 0, 1, or any fraction between 0 and 1 will do the job here, right? Like 1/2, all of those things. Are we good with number 1? Yes? All right, negate number 2. So we have the negation of that exists x such that x squared is equal to 2. What's this?
For all x, x squared does not equal to.
Very good. So a common mistake that students make, you typically you typically remember that you have to flip this and so on, but then you forget to negate this part. Make sure that you negate this. Okay, otherwise you're not telling me, you're telling me something else. Okay. Are you okay? All right. So let's see. Let's evaluate. What's the value of this?
True.
It's true. Why? Square root of 2. Good. And what's the value of this? False. Why? No, don't do that.
Just for all values, it doesn't. Yeah.
Square root of 2. When you say that a universal is false, how do you justify? Give me a counterexample. You have to give me something concrete, right? So you can either give me square root of 2 or negative square root of 2. You could say negative square root of 2. Yes? Okay. All right. Let's have fun with number 3. Oh, another rule is typically when we say to negate a quantified statement, we always want the negation to move it through all the way until it reaches a predicate. For example, if you were to negate this one, you do it here. If you're gonna negate this one, the negation of for all x, p of x implies q of x. And naturally, your first step will be, oh, this is the x6x, and then I negate this. Yes, that's naturally the first step. But then you cannot stop there because this, we need to take it inside here. Because this is not touching a predicate, this is touching this implication, this conditional statement. Okay? So you have to make sure that the negation is next to the p or the q, whichever it is, or maybe both, who knows? We have to do it. Okay? But you cannot stop here. Because now the question is, what's the negation of this? Okay? So I guess this probably really translates into how do you negate implications. We did this in the previous section. So what's the trick? How do we negate implications?
Q of x and not p of x.
Yeah.
No.
Non P of x or Q of x.
Almost. What is it?
Non P of x or Q. Close enough.
Okay, what is that?
Nah, not the first one or the second one.
Yeah, but what does that expression represent?
The same like
The implication.
yeah,
And then
and then you have to take the negative of that like
then you do the Morgan's law.
yeah.
Right? So remember, the point is that implication and biconditional, these are just nice way of saying something, but the basic operators that we have in logic are negation and or. Everything can be written in terms of negation and or. And we know how to negate and or using the Morgan's law. So your first job is to get rid of this implication. You need to turn this into a negation and or statement. Once you have that, then we know how to negate. Okay? So you need to remember, what's equivalent to P implies Q? That's another way of saying this. It was not P or Q. That's a very important identity that you need to remember. Okay, when we discuss logical equivalences. So recall that P implies Q is logically equivalent to not P or Q. Okay? This is your recipe in breaking an implication into an or statement. If you had a biconditional, what's the recipe? Let me put it here just as a reminder. If you had a biconditional, what's the recipe of breaking a biconditional?
P implies Q and Q implies P.
Two conditionals.
So you write as P implies Q and Q implies P, and then each of these you use the previous recipe to break them into negations and ors. Now you're going to have negation or and, the basic operations. Then you do what you need to do. For example, this was an if and only if, you have to play a longer game. You have to do this, then break each of these like this, and then you negate that bit. Okay? All right. So let's do it. So that means that now we can rewrite this as that exists x such that we have the negation of. All I'm going to do is rewrite that implication with the or statement. So it will be not P of x or Q of x. Yes? And now we negate. This is an or statement, and we know how to negate or statement. The Morgan's law. What does the Morgan's law says? How do we negate an or statement? It turns into and we negate both. Right? So this becomes the 6x such that, so let's see, this is an and here. So what's the negation of P? P. That's just P. And then here, negation of Q. So you know, almost. I just say not P and Q. It's the other way around. Okay, questions. And now here we stop because now we have our negation touching, you know, the predicate function. That's it. There's nothing more we can do. Okay. Questions? So that's how you negate quantified statements. Okay. Are you okay with this? All right. So that was that, and then we have seen examples of just one quantifier. But there is no need to have just one quantifier. You may have nested quantifiers. So, and typically in mathematics, you know, typically you're talking about 2 or 3 things. So whenever you talk about 2 or 3 things, you're going to have a quantifier for each of the variables that you're talking about. Okay? So let me talk about that. So nested quantifiers. Like the name suggests, what does the name nested? What does the word nested means? One inside the other, right? So nested quantifier is when you have one next to the other. In other words, when a quantifier is inside the scope of another quantifier. We defined this word scope last time. It's the portion of the statement that a quantifier acts. So let me write that down. Remember, here we are building a language and a way of thinking, okay? So then we can move forward. So that's why there are a bunch of, the whole course will just be a bunch of definitions, and then here and there you may have a couple of theorems, okay? We're building a language. So 2 or more, could be more, okay? Or more quantifiers are said to be nested. Find this. If one is in the scope of the other. Is in the scope of the other. Okay, so let me give you an example. So you see what visually you will realize it immediately because you see one next to each other. You're gonna see the 2 quantifiers. So let's see. For this, I'm gonna say the domain because then later we're gonna want to evaluate the expression. So let's say that the domain is a real numbers. Let's just say the reals. And then here are my examples. Let's see. For all x, that exists y, such that x plus y is equal to 0. Here's an expression. Here you see 2 quantifiers, and they are nested because what's the scope of for all? All of this. Okay? And inside the scope, you have this extension. Okay? So this guy is inside the scope of for all. So this is an example of nested quantifiers. And for example, this is a way of talking about property of the real numbers. What property am I talking about here? Let's see. Again, the success in understanding this is in being able to read this in English. For every real number x that exceeds a real number y, such that when you do x plus y, it equals 0. What am I saying then? This is what it means. This is called that every number has an additive inverse. You see, 0 is a neutral element of addition. It's the only number, so that when you add it with anything else, doesn't change the number, right? You pick any other number, you add it with something else, you're gonna get something else. You're not gonna get the same number. Okay, 0 is the only guy that doesn't change anybody with respect to addition. That's called the neutral element. What's the neutral element of multiplication? 1, right? Not every number field has this type of properties, like any number system has this type of property, okay? But okay, 1 is a neutral element of addition. So here we are saying that the real numbers enjoy this property of having an additive inverse. In other words, no matter what number you have, you will always be able to find another number, could be the same, like in the case of 0 is itself. You can find another number so that when you add them, you get the neutral guy. In other words, the systems of negatives. If I give you 30, you know that there is a special number that give you, when you add it, give you 0. What is it? Negative 30. So this is really talking about the existence of negatives. Okay? A negative number is just the additive inverse of its partner. I don't want to say its positive version because what's the additive inverse of negative 30? 30. Because the property is something that when you add it, you get the neutral guy, which is it. for example, with respect to multiplication, and let's say that we're talking about integers. Like this property also holds, if I say here the integers, this is still true, right? And now let's talk about multiplication. You have to be careful with multiplication on the integers. What's the neutral element in multiplication for the integers?
One word each.
Still 1, right? 1 is a neutral element. Anything times 1 is equal to itself. Now, can we say if we have the integers and if I put a times in here, would that now be a true statement? Is it true that every element has a multiplicative inverse? No, because then you will get fractions. That's what fractions are. Okay? That's how people thought about rational numbers, because they wanted to have, they say, oh, we have additive inverse. I want to have a multiplicative inverse. But the integers are not enough for this. You cannot have, if you have 2, there's no number times 2 that gives you 1. Unless you think about other type of numbers. If you only want to count stuff, you cannot find a multiplicative inverse for 2. So the concept of a 1/2 comes into play. Now you need to expand your number system. Okay? So all of these properties, this is how you write them formally, using multiple quantifiers. For every x, that exists a y, such that when you do x plus y, you get 0. Yes? All right, that's an example. And we're gonna, okay. Now I'm gonna write this. That x is a y for all x, such that x plus y is equal to 0. That's also an example. Okay? I'm gonna write more stuff, and then we're gonna come back and we're gonna see where these things are true or false. We're gonna find the true value of these things. Okay? Like I said, the success in being able to do that is in being able to read this in English and understand what you're reading. And then when you read it out loud in English, like when you say the actual sentence in words, you will know whether it's true or not most of the time, unless it's something complicated that then requires a proof. Okay? That's what theorems are. But these are really properties in a sense. So for all x, it doesn't mean that the quantifier has to be different. They could be the same. That you could have 2 for alls, one inside the other. Okay? For all x, for all y, x plus y equals y plus x. I could say that x is an x and that x is a y, such that x minus y equals y minus x. I could say for all x, for all y, for all z, x plus y plus z equals x plus y plus z. It's the reason why I'm writing this. These are not random examples. Does anybody recognize this? What's the name of this? What am I saying here? What am I saying here? This is the associative property of addition. This says that when you're adding numbers, you can add in whatever order you want. You will get the same answer. Like if you have 2 plus 3 plus 5, you can put parentheses where you like. You're gonna end up with the same result. You could do 2 plus 3 first, and then the result equals to 5. Or you could do 5 plus 3 first, and then the result you do plus 2. What we're saying here is that regardless of the order that you choose, you will get the same thing. That's called associativity property. You're free to put parentheses however you want. Not everything has this advantage. Like for example, subtraction is not associative, right? So, all right. Anyways, so let's see. Let's go ahead and let's decide. These are examples of nested quantifiers. So you have more than one inside the other. It should be very clear when you see it. Now let's figure out the truth values of these. Let's see. Let's go back to the first one. Is this true or false?
True.
True. Why? What type of a statement is this? Is this a universal or existential statement?
Nested.
It's nested, but it's a statement. So what is it? Is it universal or existential? The first quantifier is the one that tells you the type of statement this is. This is a universal statement because this is saying something for every real number else, right? What's saying? Okay, then it's saying something existential. But originally, this is a universal, so this is a universal statement, okay? So you need to argue that this is true, you need to make sure that you convince me that no matter what number you pick, you can always find another one, so when you add it, you get 0. right? So you have to do a universal argument. Now, here, there's really nothing to argue. You say it's a property of the real numbers, right? Because basically all we're saying is, or if you want to write a little argument, you just say prove, let A be any real number, All I have to do is for any real number, I just need to show you the existence of such a y, right? What y are we going to pick? What should be a y? Negative a. We know what this means, right? Then put y equals negative a. It's a real number, and then when you do a plus negative a, what do we get? We get 0. That's it. Done. We just showed that no matter what real number you have, we can find another one that is just. Okay? But because this is so simple, you can just tell me that's a property of the real number. So move on. Okay? All right. Number 2. Is it existential or universal? The reason why you need to know what type it is because then when you are about to justify, it tells you how to do it. Okay? For example, it's existential, so to justify this, what do you need to do? You need to exhibit a y. You need to just give me a y, an example. A y. The problem here is that it has to be a y that works for every x. Okay? Notice that there is, okay, let's first do this. So let's read it. This is saying that exists a real number, it's called a y, so that no matter what real number you take, when you add them, you get 0. That's what this is saying. Do you agree with this? There is a y, so that for all x, x plus y is 0. So we're saying that there is a number, so that no matter what other number you pick, you will always get 0 when you add. What do you think?
It's true.
This is true? What is that number? Let's see. Think about it. Here we're saying there exists a number, so that no matter what other number you pick, when you add it, you always get 0. It's different because here I'm saying first I'm letting you pick whatever number you want, and then I come and I tell you the number that will cancel. Here I'm picking a number, and I'm claiming that no matter what you say, my number will cancel your number. And you know this is not gonna work, right? No matter what number I pick, you can always find something that my number will not cancel. Because I'm picking first. Here the question is who is picking first? Who gets to pick first? You understand this? Moral of the story. The order of the quantifiers matters. Okay, so here it looks the predicate part is the same. The only difference is that we have for all first in number 1 and then there exists, and then here we just switch the two quantifiers. Yes? But all of a sudden we get a completely different statement. This is false. Okay? Now, the trouble with this is that to justify that an existential statement is false, you need to do a proof. Because you need to show me that there is no such number. There is no such y with this property. So you need to argue that no matter what real number you pick, this part right here is not going to hold. Okay? And that's where the ingenuity may come in the proof. So I guess let me show you quickly. So proof of number 2. So remember, the statement says there exists a y such that for all x, x plus y equals 0, and we're claiming that this is false. Okay? All right. So how can I argue this? I'm going to argue that no matter what y you pick, I will always be able to find an x so that this is not going to work. If I do that, then we're good to go. Because remember, we want to negate this part. So to contradict this part is to say that there exists an x so that this doesn't work. Right? What's the negation of this little piece? That exists an x such that x plus y is not 0. So that's what I'm going to be looking for. No matter what y you pick, I have to let y be arbitrary because I want to show that there is no such y. So no matter what y you pick, I will show you an x that will make this not true. Okay? If I do that, then our argument goes through. So do you understand the logic behind this? Remember that when you argue that an existential statement is false, you need to do really a universal proof. Like you need to show that no matter what element you have, the property that you're claiming does not hold. Okay? So you need to pick an arbitrary element. If you said that it was true, then you just need to show me why that works. Okay? But we're saying it's false, so we need to argue. So let A, I'm using A just to get away, but you can think of why. But let A be any number, be any real number. Okay? I'm going to show that no matter what number A you pick, I can always construct an X. That when you add them, you don't get 0. Okay? Here is where the thinking gets involved. What I'm about to do is not necessarily the only thing that you can do. You can do all the stuff, but I'm just going to do what comes to my mind, which is the following. So pick, of course, whatever number I build, it has to be based on A. If it's not based on A, then how are the two things related? Okay? Because remember, you're free to choose whatever A you want. So I want my answer to evolve with the A. If you pick a 3, I do something. If you pick a 4, I'm going to do the similar thing, but about 4, not about 3. Okay? So my answer, my expression now will depend on A. So pick an A, let A be any real number. Then I'm going to say, okay, pick X to be A squared plus 1. Nobody can stop me from doing this, right? If you pick a number, this is a real number, then A squared plus 1 is also a real number. Do you understand this? Like take your number, square it, and do plus 1. Nobody can stop you from doing that. This is a real number. Then let's make sure I'm claiming that this number contradicts this. Okay? So then what is A plus X? This is A plus A squared plus 1. So that would be, that's the same thing as A squared plus A plus 1. And then the question is this equal 0? I want to show that this is not 0. Okay? Now, what is this? This is a quadratic expression in A. Yes? And remember, what is our domain? Real numbers. So for this to have a real solution, so the question that we're asking is, does this have a real solution? When do quadratic equations have real solutions? There is a special component that you learned back in college algebra that tells you this. Do you remember the quadratic formula? Remember the stuff inside the square root? What is that stuff inside the square root? B squared minus 4AC, that's called the discriminant. The sign of that number tells you. If that number is positive, you're going to have 2 real solutions. If that number is 0, you're going to have 1 real solution. If that number is negative, what solutions do you have? Complex solutions, because you have the square root of a negative number, right? So to figure this out, you look at the discriminant. So the discriminant, and okay, unfortunately I'm using A, but the A is not this A, it's the coefficient, okay? So the discriminant, do you know what I'm talking about when I say discriminant? So let me just do a little parenthesis here. So recall, when you have a quadratic equation, ax squared plus bx plus c equals 0, that's a quadratic equation. Please understand the scope. This A is not that A, okay? So ax squared plus bx plus c equals 0 is a quadratic equation. Then the solutions has 2 solutions and is negative b plus or minus the square root of b squared minus 4ac over 2a. This is what we call, the quadratic formula. And in this formula, this guy right here tells you what type of solution you are getting, because you're doing the square root of this. So if this is a negative number, you know that your solutions now are complex because you're doing the square root of a negative. Okay? So the sign of this tells you the type of solution. So it has real solutions if the number d, which we call a discriminant, which is negative b squared minus 4ac, is greater than or equal than 0. Okay? Otherwise, they're complex. Otherwise, they're complex. Okay? So that's what I'm going to tap into. Remember that here ABC stands for the coefficients. What are the coefficients here? Our variable here is A. So what are the coefficients? 1, 1, 1. Right? Everybody's 1. So let's compute the discriminant. So it will be 1 squared minus 4 times 1 times 1. Yes? So what is this? That's -3, that's less than 0. So what does that mean? No real solution. Right? So there is no real number that will make that work. In other words, a plus a squared plus 1 is different than 0. We're only working with real numbers. That's our domain. Okay? So we just did it. No matter what number you pick, I was able to construct another one so that when you add them, you don't get 0. So that statement is false. Because there's no number that acts as an additive inverse for everybody. Okay? Notice the difference from the first one. The first one says, no matter what number you pick, I will find then your additive inverse. So you're doing the second, so you have the advantage because you know what he's picking. But if you don't know what someone is picking, you cannot tell beforehand what the additive inverse is. Yes?
Can you substitute x equals -a plus 1?
-a plus 1. You have to be careful because you have to make sure that it works for everybody. So let's see, a, and then plus -a plus 1. Okay, good. Because these two guys, they cancel out and you get equal to 1. Good. That's why I said, it's not necessarily, yes, I wanted to bring these things and remind you of this. But yes, good. So if you pick this for x, that also works. Because once again, it's equal to 1. Because we are talking about real numbers, okay? But be careful. If we're talking binary, we only have anyways. Yes, this works. This perfectly works because domain is real numbers. Yes. Do you understand this? Okay. I just want to show you that sometimes you can get creative. Okay. Okay. Good. All right. So we have. Hopefully, with these two examples, you can see that the order matters. Okay. It's not the same. It matters who comes first. Now let's look at this one. Is this true or false? Do this quickly. This is true. That's a property of real numbers. That's commutativity. You can add however you want. It means that no matter what two numbers you pick, the order doesn't matter. How about this one?
False.
What do you think?
False.
False? Why? Really? This is saying there exists a number x and there exists a number y, so when you do x minus y, it equals y minus x. This is never telling you that x and y must be different. It could be the same. If you want it to be different, then I have to say there exists a y different than x, so I will have to have a statement. X is different than y and this. Okay? But if it doesn't say that, you cannot assume that they are different. Okay? Yeah. So if you pick x equals y, this will always work. Do you understand this? So this is true, and then you can say just give me a concrete example. I don't know, x equals y equals 1, or whatever is your favorite number. Okay? You okay with this? All right. This is an existential, so I just need to give an example to justify why it's true. Number 5. True. This is true. Again, this is the associativity property, right? Now, the summary here is the order matters. Now, notice that if I were to flip these two, will that change the truth value of what we have here? No. And if I flip these two, no. So if you only have for all or only have that exists, it doesn't matter. You can flip them, doesn't change the value. Now, if you have a mixture of them, for all and then they exist, you flip them, you're changing the statement. Okay? They don't have to have the same value. So let me just write that down and then we call it a day. So theorem for all x that exists y, and let me say p of x comma y. So statement is not the same as that exists y for all x p of x1. Sometimes it could be the same, but in general, it's not the same. Okay, and the proof for this is here you have the two concrete examples, 1 and 2. Okay, and then the other cases are fine. So you have for all x, for all y, p of xy. This is the same as for all y, for all x, p of xy, and similarly with existential. Okay.
Is that x Sub one or is it X comma Y? No.
Which one? It's P of X comma Y. This is a predicate.
Right.
Two-place predicate.
Just making sure.
Yes.
So Professor, if the predicate doesn't matter, even if you flip them?
Then you have to keep the same predicate. I mean, you change the predicate, you're changing everything. Right? Like for example, here, if I don't touch this parenthesis, but I just flip these two, I mean, X and Y here are really dummy variables. I mean, they don't really, because it's for all X, for all Y. So X represents any number, Y represents any number. So thinking about it, it doesn't really matter which one comes first. We're talking about any number. Right? So, but here, it matters. Okay? All right, guys. So with this, we're good to go. The only thing is how to negate nested, but you already know how to negate quantified. Nested, just pass it through. Like if you negate this, what will it be? There exists an X, so that for all Y, X plus Y is not zero. Right? You just keep passing the negation through until you hit your predicate. Okay? Following the rule that if you hit a quantifier, you flip it. Okay? That's all. All right, so next time, we're gonna talk about inference rule, arguments and inference rule, and then we do proofs. Okay? And then that will be the end of logic for the exam, which will happen not next week. I think I already moved in the calendar. I'm expecting that to be following week. Okay? So we can still have one more week of content, and then we do our exam. All right. Let's see.